Okay. So thank you. Yan Wei will give us a graduate talk on the stability-based online access resource slicing in HRUN. So thank you for anyone coming this graduate talk. And Yan Wei, you can start show your slides.
Okay, thank you. So everyone can see my slides, right?
I believe so.
Uh, do you can see my slides?
I can see your slides.
Yes, yes, yes.
Oh, yeah, okay. So good morning, everyone. My name is Yanan. I'm now a first year PhD student supervised by Professor Zhuang. I'm glad to be here to give a talk on the topic stability-based online access resource slicing in HC-RAN. This title is a little different from the one emailed before because I think this title is more appropriate to the content that I will share next, but the core contents are the same. My presentation will be delivered following this online. First, I will briefly review the background of the access network resource slicing and identify its challenging research issues in the resource management, which I need to be further investigated. Then I will elaborate on a specific example and show some theoretical and simulation results to analyze the proposed schemes. Finally, I will conclude my speech. So from a service-oriented point of view, next generation wireless networks are anticipated to support multiple use cases simultaneously from vertical industries with differentiated communication demands in terms of data rate, latency, and security. ITU has identified three typical application scenarios for the next generation wireless networks. That is the enhanced mobile broadband (eMBB), ultra reliable and low latency communication (URLLC), and the massive machine type communication. These three uh, different application scenarios have distinct quality of service requirements, uh, which can be shown by the figure right. To realize the vision and address the resulting challenges, the network slicing has been proposed as a promising solution, which is enabled based on the virtualization software-defined networking and the network function virtualization (NFV). In addition, the wireless resource sharing among different slices is a critical challenge due to multiple reasons. First, the characteristics of slicing, which are customization on demand, dynamic scalability, and specific QoS provisioning, put forward higher requirements on the flexibility of wireless resource allocation. Second, dynamic slicing forces operators cannot still construct network slices with static information. It is necessary to consider the impact of current resource management decisions on the creation of new slices and the run quality of all slices in the future. Therefore, how to correctly derive the resource allocation decisions in dynamic slicing setting is a critical topic. To achieve that, the network operator need to maintain an accurate depiction of resources that are currently in use and their availability over time. A challenging problem therein is to model the resource utilization as a time-evolving process. This methodology creates an arena of online optimization problem. Here, the so-called online means that the system dynamically adjusts its wireless resource management strategy in time according to the current network status, including the channel conditions, queue lines, traffic loads, and available resources, and optimize the system performance on a large time scale. In general, typical tools for modeling and solving the online optimization problems include one is using the offline optimization counterpart in two subsequent phases. First is the quick assignment and then readjustment the local policy and the near optimal policy. Another is the bandwidth calendaring. Besides, the stochastic optimization techniques are also well applied mathematical tools such as Markov decision process, Lyapunov optimization, and large deviation theory. Next, I will focus on a specific case study which investigates the joint admission control and resource allocation online scheduling for access network resource slicing. Specifically, the system model is a downlink transmission scenario of heterogeneous C-RAN shown by this figure, and we consider the coexistence of EMBB and URLLC applications with differentiated requirements, which will be elaborated more specifically later. Assume that the traffic arrival is bursty and random. That means we don't have the statistic information of traffic model in prior, and the network may fall into the congestion states once the random traffic arrival rate exceeds the network capacity range. In addition, assume that the remote radio head RRH cooperatively transmit to the C-RAN users with maximum ratio combining at the receiver to improve the data rate. Also, consider for any subcarrier, it may be reused between RH and the high power node HPN for higher spectrum utilization. Specifically, K is the set of all RH, S is the set of available subcarriers, and we denote by U the set of all users, where C and H are the set of users served by RH and HPN respectively. What's more, let binary variable alpha lowercase s be the subcarrier reuse indicator, and beta SC, beta SH are subcarrier allocation variables for the C-RAN user, CUE, and the HPN user, HUE, respectively. Then the instantaneous data rate for user U at time slot T can be calculated as the equation. In addition, assume that each user has a buffer to temporarily store packets that have not been sent out yet, and the queue of each slice user updates over time following this evolving equation, where the lowercase r u denotes the amount of data allowed to be admitted at time slot t, namely the traffic admission control. Furthermore, we consider different correlative service requirements for different types of slices. For the EMBB slice users, the network should satisfy the minimum instantaneous data rate at any time slot. Then for URLC slice users, we consider the correlative service demand in terms of reliability. That is, for any user, its ISINR on any subcarrier should be larger or equal to the given threshold. Overall, the considered problem is formulated as a stochastic optimization, shown below, which maximizes the average total throughput as the objective, while subject to constraints, where the constraint C10 is a system stability constraint to guarantee the network stability. In the following, for this problem, we first transform the original problem with time average objective into an equivalent one within each single slot by leveraging the Lyapunov stochastic optimization framework, and then propose an online resource allocation algorithm with system stability and QoS guarantee for multiple resource slices. Specifically, according to the Lyapunov stochastic optimization, the original problem can be converted to this single slot problem subject to the same constraints except the stability one C10 mentioned before, where the V is an introduced control parameter. This single slot problem actually can be seen as a weighted sum minimization of instant queue backlog and instant total throughput, which also can be interpreted as a joint trade-off optimization between the system stability and network performance. For this single slot problem, we can further decompose it into two independent subproblems: the traffic admission control and the wireless resource allocation, respectively. For traffic admission control subproblem, we can easily obtain the optimal strategy. And by solving this subproblem, we can find that it's a threshold-based admission control scheme. For wireless resource allocation subproblem, its corresponding Lagrangian function can be written as this formula. Observe that it can be further decomposed into capital S independent subproblems, each for a particular subcarrier. That means we can allocate those subcarriers one by one. For any subcarrier S, the resulting exclusive subproblem is described as follows. Furthermore, from the constraints C1 to C4, we know that for any subcarrier S, it can either be orthogonally allocated to only one user, or it can be reused and assigned to one CUE and one HUE simultaneously. Therefore, the allocation for any subcarrier S falls into one of the 8 categories below. By comparing the optimal objective function value under each possible situation, the final decisions on subcarrier reuse, the resulting subcarrier, and the power allocation for each subcarrier in current time slot can be determined. Furthermore, in solving each possible case for any subcarrier, we basically utilize the QTT conditions or propose a particle swarm optimization algorithm with similarity-based mutation to find the near optimal solution, and we omit this part due to the time limitation. Finally, we propose an online resource allocation algorithm with system stability and QoS guarantee, shown in this table. Next, I will show some theoretical and simulation results to validate the effectiveness of the proposed scheme. First, utilizing the Lyapunov stochastic optimization theory, we can derive the performance bounds in terms of the instant queue lines, the average total throughput, and the average queue lines, respectively. It can be seen from the first and the third items that the proposed algorithm can maintain the network stability. More importantly, the second and the third item reveals that there exists a V and 1 over V trade-off relationship between the average delay and the average total throughput. That is to say, we can flexibly adjust the value of control parameter V to achieve dynamic balance between delay and throughput. Here shows some simulation results. This figure depicts the average queue lines over time slots. It can be seen that the average queue lines will gradually converge to a steady and finite value, which proves that our proposed algorithm can effectively maintain the network stability. What's more, a higher quality of service requirements will result in a longer average queue lines, but with a faster convergence rate. These two figures show the effect of control parameter V on system performance. We can observe that as the value of V increases, average total throughput will approach the theoretical optimum at a rate of 1 over v, and the average queue length will almost linearly increase with the rate of v. This means that there indeed exists a v and 1 over v trade-off between the two metrics, which coincides with our previous theoretical analysis. Therefore, as stated earlier, we can choose the appropriate v value based on our needs to make the system work in the desired performance status. Finally, I will conclude my presentation. First, we discussed the challenges in resource sharing among heterogeneous resource slices and identified the important role that online optimization may play. Then we talked about a specific case which investigated the online resource scheduling problem among slices with differentiated QoS demands, and where an online resource allocation algorithm with system stability and a QoS guarantee is proposed. The proposed scheme could improve the network average total throughput while maintaining the stability. Besides, it could also flexibly strike a dynamic balance between delay and throughput by simply tuning an introduced control parameter, which is V. That's all for my presentation. Thank you for your listening.
Thank you for your very nice presentation. And any question from the attendants? So I have a question on the page you show the parameter v. I think the page before the last page, the simulation, yeah. So is that for the convergence rate? The O, the big O?
No, no. The O means the order.
Oh.
Yeah, like when you analyze the computation or time.
Oh, it's a computation.
Complexity.
Oh, it's computation, not the convergence, right?
No, it just indicates that the performance metrics such as average queue delay linearly increase in the order of V.
Oh, it's like the I saw that was the computation or the convergence rate, yeah, because I see the big O. So never mind. So how you when you do the do like design, so how you choose those two way? Could you talk more? How you choose the two? One is the 1 over V, another one is V. So how you choose those two optimal in the practical design? So could you talk more about that?
Yeah, of course. So I will use these two figures shown here to make an example. As you can see, the first figure shows the variation of average total throughput with the value of V, and the average total throughput will approach the theoretical optimum at a rate of the order of 1 over V. So in contrast, the bottom figure, the average queue delay will linearly increase with the rate of the order of V. So if we want a system to work in a desired status, we can choose appropriate V. Here, for example, we can choose V as the V to be the 16, so that we will have a near optimum performance. We will have a near optimum performance about the average total throughput, and at the meantime, the average queue delay is not that much. So if we continues to increase the value of V, the increment of the average total throughput will be very small, but the delay will increase intensively. So we must choose a appropriate value of V, so the average queue delay is tolerable, and we also can get a better performance like the total throughput at the same time. We can't randomly increase the value of V because the average queue delay will increase dramatically.
Oh, okay, thank you for your answer. It seems like when we equal to around 16 or 17, and it seems really efficient according to throughput and the corresponding cost.
Yeah.
So, yeah. Any question from the audience?
I have a question. Hello.
Okay, go ahead.
Okay.
I can
Can you
hear
turn to page 17?
17. This one.
Yeah. You mentioned that the second bullet, a higher QoS requirement will result in a longer average queue length, but with a faster convergence rate. But why? Can you explain about why the queue is longer queue length and will result in faster convergence rate? I'm not. I don't know why is that. Can you explain something?
Yeah, of course. So from this, first, this conclusion is derived from the simulation results, and it can be also illustrated or explained by the in a theoretical way. First, from the simulation figure shown here, the black curve, the black line is simulated under a higher quality of service requirement. And that is the minimum required instantaneous the minimum required the signal to and the interference to noise ratio is 3.5 and 100 for the EMBB slices and the URLC slices respectively, and wait a minute. Okay, from this page, I can explain this better. So this transformed single slot optimization, as I mentioned before, it can be viewed as a waiting sum minimization of instant queue backlog and instant queue throughput. So if we, in my opinion, if we increase the quality of service requirement, that means the system has to put more efforts and resources to satisfy the constraints of the quality of service requirements. First. So it will since there are a lot of optimization parameters needs to which are coupled and turn this single slot optimization problem into a very complex one. So with a higher quality of service requirement, the system will put more time and more effort to try to find a near optimal solution under the constraint with the scope of constraint. So the convergence rate
do you have some theoretical analysis about the convergence performance or convergence rate? So this conclusion is only based on your simulation results or some analysis?
Oh yeah, this conclusion is more based on my simulation results. Well, I start with the simulation results and try to analyze the background reasons that can derive this results.
Yeah, I
So
just you can go ahead.
On my defense, I think the higher qualitative surface requirements will force the system to put more resources, to use more resources to satisfy the QoS requirement first, like the data rate requirement or the reliability constraint. So the system stability will not be considered in priority. The thing the system needs to do is to maintain the system's stability just fine. It doesn't need to guarantee the system stability in a high level. So when there are multiple, when there are redundant resources, the system will use the resources to satisfy the higher QoS requirement first, then to consider the level or the degree of system stability.
You mentioned guarantee QoS requirement first, right? Or QoS right? It guarantee QoS requirement first, then guarantee the stability. That's what you mean?
There is a little misunderstanding. In the problem formulation, you can see that the constraint C7 and the 9 are the QoS requirements for different slice users, and the C10 is the system stability constraint. What I explained before is try to see that if I must make an example, with a lower quality of service requirement, assume that the system stability is guaranteed with the average queue length, say for 100, but with a higher QoS requirement, when there are more resources or enough resources, the system has to satisfy the quality of service requirements. First, because it's a tougher condition to for the problem, and in this case, although the system stability is also maintained, but the performance, the level of the stability may be reduced. So before the system stability, the average queue length is 100, and with a higher quality of service requirement, the system stability is also maintained, but with the average queue length becomes 200 or 300, but it's a finite number. The average queue length is still a finite number, means that the stability is always guaranteed, but the performance, the level of the stability is reduced because the more resources is taken for the system to guarantee the more strict QoS requirements.
Okay. Thank you for your explanation. Just curious about the relationship between the average queue length and the convergence rate. Okay, thanks so much. I have no more questions.
So any more questions from the audience? You may see it on the chat box. That's also so thank you first for your attending this graduate seminar. And every time we have an evaluation form for you to show your opinion, but because right now it's a COVID-19 period, so we cannot collect the real form from you guys. So we upload and the empty form online, and you may see it from the chat box. And we will really appreciate if you can download it and finish it and send back to us. So it's really important for us and the Yan'an. So thank you so much for your attendance, and I thank you in advance if you can finish that form. And so maybe if we don't have more questions, we can stop here. Okay, so thank you a lot for your attendance.